In this lesson, we're going to continue talking about solving trig equations. So for this lesson, we're going to see some examples that are just a little bit more complex. So we might have to use those trig identities first to substitute in, and then we're going to see some factoring involved. So when I first look at this problem here, I see that I have cosine as well as sine for this. So my first step is I need to get this in terms of one trig function. So since I have a cosine squared, if you remember, whenever we have a cosine squared, that's kind of like your red flag that you want to be using the Pythagorean identity. So sine squared plus cosine squared equals 1. So what I can do is I can replace this cosine if I rearrange this Pythagorean identity. So meaning if I subtract sine squared from both sides, that'll give me cosine squared theta, which is equal to 1 minus sine squared theta. So then I can replace this cosine with that 1 minus sine squared theta. So I'm going to keep the 2 out in front. And instead of cosine squared theta, it's going to be 1 minus sine squared theta. And then I'm going to keep the rest of this. So minus sine theta equals 1. So then as soon as you see a squared term, that tells me that I'm going to be having to factor. So before I actually go and do that, though, we do need to distribute. So we have 2 minus 2 sine squared minus sine theta. And I'm going to go ahead and bring over that 1 as well, because remember, we're going to have to factor, so we have to have 0 on one side. So I just brought that 1 over. So now we can combine our like terms. So we have 2 sine squared theta minus sine theta, and then these are going to combine. So 2 minus 1 is just going to give me plus 1 equals 0. And now when you go to solve this, you want to never have negatives in front of like your squared term. So think about like if you have a trinomial, like an x squared plus an x plus a number, you always want to have a 1 out in front of that x squared, or at least not a negative number. So right away I'm just going to divide out by a negative 1 because I want to get rid of the negative sign in front of this. So as long as I divide everything by negative 1, you're allowed to do that. So I end up with 2 sine squared theta plus sine theta minus 1 equals 0. So now what I need to do is I need to factor this. So again, remember, you can think of this as 2x squared plus x minus 1 for the factoring part of it. So that's probably the easiest way, is to turn it into x's first, figure out the factors, and then just convert it back to sine theta. So what I'm going to do to factor this is we multiply these two terms, and we need to find a number that's going to multiply to negative 2, since 2 times negative 1 is negative 2. So it's got to multiply to negative 2, but then it's got to add to this middle number, which is 1. So the numbers that are going to do that, multiply to negative 2, but add to 1, are going to be 2 and negative 1. So those are going to be my numbers that I'm going to use to rewrite this middle term. So what ends up happening, so because we're doing a factor by grouping, I can't just do add multiply because I had a number other than 1 in front. So that's why I multiplied those, and that's my multiply to number. So I get 2 and negative 1, and what I do now is I rewrite this middle term. So instead of having an x, it's going to be plus 2x minus 1x, and then I keep the minus 1. So this middle term became, I just expanded it basically. So 2x minus 1x gives me that middle term. So I expand it so that I have 4 terms so that I can do factor by grouping. So now this I can take out, there should be a squared there. So now I can take out a 2x. So I'm left with an x plus 1. And then here I can just factor out a minus 1, and I'm left with x plus 1. And now since we have the same factor, we can factor that out. So x plus 1, 2x minus 1 equals 0. And now back over here, I can go ahead and instead of having the x's, I can replace this as sine theta. So instead of x, it's going to be sine theta plus 1 and 2 sine theta minus 1. So once you figure out your factors, just plug them back in for x, and then you just have to solve these like we did in the last video. So split it, set each part equal to 0, and then you're just solving for theta. So this one we have sine theta equals -1. This one we have 2 sine theta, bringing over the 1 gives us 1. Divide both sides by 2, we get sine theta equals 1/2. So for this one, since it's equal to a -1, let's look at our graph for this one. So for sine, we have 90, 180, 270, 360. Sine is going to start, so if we go up to 1, down to -1, sine's going to start at 0, 0. It's going to go up. It's going to come back down to 0, 0. It's going to go down to -1 and then back to 0, 0. So there's your common sine curve. So if we're trying to find when sine equals -1, that's right here, which is at 270 degrees. So this is going to be at 270. And remember, for this particular one, we're trying to solve between 0 and 360. So I'm leaving my answers in terms of degrees. So there's one answer. Then we move over to this one, and basically the easiest thing to do is just to find the reference angle. I wouldn't even worry about taking sine inverse of both sides because you need to find the reference angle to be able to find both angles. So to find the reference angle, you're going to take theta, well, the reference angle will equal the inverse of whatever this number is, sine inverse of 1/2. So you always just take sine inverse for the inverse function of the positive version of whatever that number is, and that'll give you the reference angle. So the reference angle equals this. So what happens is you're going to get a reference angle of 30 degrees. And then what you want to do is on your 4 quadrants, all students take calculus. Our answer here is positive, so that means I'm looking at where is sine positive. So it's positive in these 2 quadrants, so that's where my reference angles are going to be. So they're coming off of the horizontal axis. So I have 30 degrees, 30 degrees. So for solving this equation here, one of the answers that will solve this equation is going to be the 30 degrees. And then the other one is going to be 180 minus 30, which is going to give me 150. So that means overall my solutions to this problem are going to be 30, 150, and 270. You just include all of the answers. So that's definitely a more complex one, but the process is the same. It's just the algebra becomes a little bit more difficult. So let's look at a couple others like this. This next one isn't too bad, but we do have some factoring or some factoring techniques involved or some solving quadratics involved. So basically I look at this, and remember you can kind of think of this as 3x squared minus 1 equals 0. So you try to factor because it has an x squared in it, but you notice that there's no common factor between these two terms. So basically what that means is you just solve this and get x by itself. So you're going to end up bringing the 1 to the other side, divide both sides by 3. So we get x squared equals 1/3, and then you just end up square rooting both sides. So that's where we're going to go with it. So we're going to do it, except for we're going to do it with tan in there. So I'm going to bring the 1 over. So 3 tan squared equals 1. Divide both sides by 3. So tan squared x equals 1/3. And now you're taking the square root of both sides. So we end up with tan x, because when you square root it, and when you square root a variable, you got to remember this plus or minus. So again, it's going to be Square rooting a tan squared is going to leave you with 1 tan. And you got to remember the plus or minus square root of 1/3. Now, the square root of 1/3, if we were to rationalize that, so let's just say we have 1/3. This is the same thing as saying the square root of 1 over the square root of 3, which is the same thing as saying 1 radical 3. So then what happens is we want to rationalize that. So if we have 1 over radical 3, to rationalize, you multiply the top and bottom by radical 3. So the top becomes radical 3, and then the bottom is just 3, because radical 3 times radical 3 is 3. So really what this becomes then is tan x equals plus or minus radical 3 over 3. So that means I want the answer from all 4 quadrants, because I want the positives and the negatives. So when I look at finding my reference angle, I'm taking tan inverse of, we always take it of the positive for the reference angle. So you take the tan inverse of both sides but make it positive to get the reference angle, which is going to give you a reference angle of 30. So then when you go to look at your quadrants, all students take calculus. Tangent is going to be positive here and here. But we also want it where it's negative as well, because tan of x is equal to positive and negative. So this is where tan is going to be negative. So really I want my reference angles to be drawn in all 4 quadrants. So here are my reference angles. So that means I want 4 different angles here. I want this 30 degrees. I want this angle here that's formed. So far x is going to equal 30 degrees. This one's going to be 150, 180 minus 30. Then I want this angle, so it's going to be 180 plus the 30, so 210. And then I want this big angle that goes all the way to here, which is going to be 360 minus the 30, so 330. And then those are going to be your solutions for this. So we use both positive and negative. This problem here too, just making a note of this, it should have told you what to solve for. So meaning to solve between, like what x should be between. So I'm just going to make a note of that with x is going to be between 0 and 360 degrees. So any of those numbers fit in that category, so that's why we'll leave it. All right, looking at number 9 then, we have a couple different trig functions here. We have a cotan and we have a cosine. So that tells me that I'm going to need to rearrange this or use my identities first before I try to solve this. So first thing I see here is I'm probably going to want to either replace this, or if I look at factoring, because there's a cosine squared in there. And actually when I look at this, I see a cotan here and a cotan here. So I could go through and replace cotan with cosine over sine. But really, if I just bring this cotan over, so meaning if I just rewrite this, I could subtract 2 cotan x from both sides, and I end up with this. And then if you look, we have a GCF here. So that means I could factor out a cotan x, and if I take that out, I'm left with a cosine squared x minus 2. And then it doesn't really matter that I have 2 different trig functions. So typically when you have 2 different trig functions, you're going to have to use those identities to plug in. But when I saw that I have a cotan and a cotan, and I could just subtract that over and get 0. And then when I factor, I take out the similar pieces. So now, since I have 2 things being multiplied equal to 0, I can just set them equal to 0 individually. and it really doesn't matter that I have two different trig functions. So if you can see a GCF or two common trig functions that eventually can factor out, you don't need to worry about using those trig identities. So then what's going to happen is I have two separate equations that I have to solve. So for this one, cotan of x equaling 0, the easiest thing to do is think of this in terms of cosine, sine, or tangent. So if we're thinking about this in terms of what cotan equals, cotan of x is actually equal to cosine over sine. So what this really means is cosine x over sine x equals 0. So in order for this to actually work, that means that the top has to be 0 because 0 divided by anything is going to be 0. So it doesn't matter what the bottom is. If we're getting out 0, that tells me that the top has to equal 0. So cosine of x has to equal 0. So essentially this turns into cosine of x equaling 0, which remember when it's solving for cosine or sine equaling 0, 1, or -1, use your curve. So the curve for this one, we have our 4 key points. So it starts up at 1. Then we have it going down to 0, down to -1, 0, and then +1 again. So my key points are going to be here and here, which is going to be pi over 2 and 3 pi over 2, or 90 degrees and 270 degrees. So I'm going to go ahead and write x equals 90 and 270. Again, this one doesn't specify where we're solving or what we're solving for. So it's going to be solving with x between 0 degrees and 360 again. So those are my two solutions. And then over here, now I have to solve this side. So what I'm going to do is I'm going to look to see if I can factor, which I can't. So I'm going to go ahead and rewrite this by bringing the 2 over and then just applying the square root method to both sides. So square root both sides, we get cosine x equals plus or minus the square root of 2. So the square root of 2 is going to be a number bigger than 1. So that means that can't ever happen. It's also going to be square root of, or negative square root of 2 is going to be a number smaller than -1. So if you think about your graph, it won't ever happen. So there's no solution to this part. So then that means the total solution for this entire equation is going to be 90 degrees and 270. Okay, so looking at this one, we see two different trig functions. We have a sine squared and a cosine squared. So look to see if you can do a GCF. If not, then we're going to have to use those trig functions. So for this one, there's no GCF between all three terms. So since I have a sine squared, that tells me I'm going to be able to use that Pythagorean identity. So sine squared x plus cosine squared x equals 1. If I want to replace sine squared, that means I can get that by itself over here. So subtract cosine squared from both sides. So I get 1 minus cosine squared. So I can replace over here. So it's going to be 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. And then we can go ahead and just solve this. So we're going to distribute. So we have 2 minus 2 cosine squared x plus 3 cosine x minus 3. Combine like terms. So I'm going to keep the minus 2 cosine out in front plus 3 cosine x. And then I have 2 minus 3 is going to be minus 1. So then it becomes very similar to that problem that we had previously where we had to factor. So again, you want to try to get rid of this number out in front of the x squared term. I can't divide everything by 2, it won't work, but I can divide everything by -1 just to get rid of the negative sign. So I'm going to go ahead and do that. So I have 2 cosine squared minus 3 cosine plus 1 equals 0. So now off to the side, I'm going to think of this for factoring. This is 2x squared minus 3x plus 1 equals 0. So I can't just do add multiply because I have a number other than 1 in front. So this is where you can multiply these. It has to multiply to positive 2, and it's got to add to the middle number. So the numbers that are going to multiply to positive 2 but add to -3 are going to be negative 2 and -1. So that tells me that I'm going to rewrite this middle term. So I have 2x squared. This is going to be minus 2x minus 1x, rewriting that middle term, plus 1 equals 0. And when you rewrite this middle term, you want to make sure that the number that you put first will have a GCF with this term, and then the number you put second should have a GCF with the last term. So you pick the order so that it works. So then we split it down the middle. We can take out a 2x. So we have x minus 1. Here we can take out a -1. So x minus 1. Now you have the same thing. So take that out, x minus 1. You're left with a 2x and then a -1. So that tells me over here that this is really going to be cosine x minus 1 and 2 cosine x minus 1 equals 0. So then we can split this and set each piece equal to 0 and solve it. So this ends up being cosine x equals 1. This ends up being 2 cosine x equals 1. Divide both sides by 2. We get cosine x equals 1/2. So for this, going back to this side, if we're trying to see when does cosine equal 1, I would say use your graph for that. So cosine, remember, starts up at 1, then it comes down, goes down to -1, back up, and then back up to +1. So it looks something like this. So if we're looking at when does cosine equal 1, well, it equals 1 here and here. So x equals 0 and x equals 360. And then for this one, you would find the reference angle, which means you have to take the inverse of the positive of this. So cos inverse of 1/2. And for this, you get 60 as your reference angle. So then when you draw your picture, all students take calculus. We're looking at when, so we go back up to this one. When does cosine of x equal a positive number? So that means I'm looking at when cosine's positive, so here and here. So you can draw in your reference angles, mark them with the 60 degrees. So the first one here is just going to be 60. So x is going to equal 60. And then for the second one, it's going to be 360 minus the 60, so 300. And if you look at the actual problem here up at the beginning, it tells us that x has to be between 0 and 2 pi. So I'm not going to include the solution because it's less than 2 pi. But these ones I need to convert them over. So my solutions here, 0 is just going to be the same thing as saying 0. I don't need to worry about the degrees. This is gone because this is like saying 2 pi, and we don't want to include 2 pi. We want to be less than 2 pi. And then for these ones, if I need to convert, remember to convert, you're going to times it by pi over 180. So this gives you pi over 3. And then the 300 degrees times pi over 180 is going to give you 5 pi over 3. So you just put the fractions in your calculator and then carry the pi through. So that tells me that the solutions to this entire problem are going to equal 0 from this one, and pi over 3, and 5 pi over 3. Okay, so the very last one here, just looking at another scenario. So this one is a little bit weird because there's nothing really right away that you can do because you can't really replace cosine or sine right from the beginning. And you have two different trig functions and you can't factor anything out. So the strategy that we can use for this one is if we square both sides of the equation, that will allow us to get sine squared and cosine squared, which if you think about it, we can turn, as long as we have sine squared, we can turn it into cosine squared so that it matches the others. Or we could take cosine squared and turn it into sine so that it matches the others. So the trick for this one, which obviously I wouldn't just expect you to know, but if you see something like this that has cosine and sine and there's no way to solve it, the trick that you can do is you can square both sides of the equation. And the reason we're doing that is basically so that we can use our Pythagorean identity. So this will allow to use our Pythagorean identity. So sine squared theta plus cosine squared theta equals 1. So that's the whole purpose. So what we're going to do is we're going to go ahead and we're going to square both sides, squaring this entire thing and this entire thing. So this becomes cosine x plus 1 times cosine x plus 1. And this just becomes sine squared x. Remember that the squared belongs with the sine because it's sine x times sine x. So now for this one, you can just set up the box because it's a binomial times a binomial. So cosine x plus 1, cosine x plus 1. So when you multiply a cosine times a cosine, you get cosine squared. 1 times cosine is just cos x. Cosine x, 1 times 1 gives me 1. Here are my like terms. So I have cosine squared plus 2 cosine. Remember, these are like x's. If you don't like doing it with cosine, just do x. X plus 1 times x plus 1, and then whatever you get, replace your x with cosine x. And now what we want to do is we want to use our Pythagorean identity. So the fact that we have cosine, cosine, and a 1 and a sine, I'm going to say that we should replace the sine squared with our cosine. So we're going to basically solve this for sine squared. So we get sine squared theta equals 1 minus cosine squared theta. We have ours in terms of x's, so really what I'll be using is sine squared x equals 1 minus cosine squared of x. So now what I can do is I can replace this with 1 minus cosine squared x. And then the other part I can just carry down. So now we have squared terms, so we need to get 0 on one side so that we can end up factoring. So what we're going to do is we can bring the 1 over, we can bring the cosine squared over. So these are gone on this side, so we get 0. These are gone. So we end up with 2 cosine squared plus 2 cosine equaling 0. So now you look to see if you can factor. Nice thing about this is it's not 3 terms, so we can just factor by using a GCF. The GCF here is I could take a 2 out of both. I can also take a cosine out of both. But remember, if this factoring confuses you with cosine, just put x's in there and factor with those and then replace it. So I can take out a cosine. Take a cosine out of here, I'm left with 1 cosine. Take 2 cosine x out of this one, I'm left with just a 1. So now we have two things multiplied together to equal 0. Split it and set each piece equal to 0. So from here, divide both sides by 2. We get cosine x equals 0. Over here, we get cosine x equals -1. So both of these are 0 and -1. So that tells me I'm going to look at the graph for this one. So 1, -1. We have our key points here. So pi over 2, pi, 3 pi over 2, and 2 pi. So for cosine, you're going to start up at 1, down to 0, down to -1, back to 0, up to +1. So when cosine of x equals 0, here and here, so x equals pi over 2 and 3 pi over 2. And when cosine of x equals -1, we're looking right here, so that's when x equals pi. Since we squared both sides of the equation, we added in a variable. So if you remember back when we did square root functions, to get rid of the square root, we squared both sides. So since you're adding in variables because you're squaring it, you're multiplying by new variables, you do have to check your solutions for this type. So if you were to check your solutions, if you plug these in, the only one that won't work will be this one here. This doesn't check. So that means my solutions to this equation would be pi over 2 and pi. And again, just check where we were leaving our solutions. We were leaving them in terms of pi, and we were leaving it between 0 and 2 pi. And make a note up here that when you square both sides, make sure you check the equation because you're adding in variables. So that's why you have to check. You're multiplying by new variables that weren't already there. So just check solutions if you do something like this, but keep in mind our solutions in the end. We cross this one off because it doesn't check. If you plug it back in, it won't work. The other two do work, so those are our only two solutions.